Welcome to this backoff webinar. In this webinar, my colleague Jannik and I would like to tell you more about our new TwinCAT S7 Communication product. Should you have questions during the webinar, we encourage you to ask all of your questions using the questions window inside of the GoToWebinar software. And we try, of course, to answer all of your questions at the end of this webinar. The TwinCAT S7 Communication product is the newest addition to our TwinCAT connectivity product family, and it allows you to establish a TCP/IP-based S7 communication with a Siemens S7 CPU. Using this product, you can read/write variables from an S7 data area, for example, from the data blocks area, from the inputs or outputs area, and it provides support for multiple CPU types like the S7 300, 400, 1200, or 1500. The product comes in two flavors. So the first flavor is PLC function blocks for the PLC programmer in order to establish a communication with an S7 CPU. And the second flavor is an easy-to-configure TwinCAT I/O device that allows you to add PLC variables from the S7 device to the process image of your TwinCAT project. So what can you do using this product? Of course, in a greenfield scenario where you maybe want to hand over parts data between PLC controllers, you can of course use this TwinCAT S7 communication product. So for example, if you have a machine that is controlled by two different PLC types, for example, a Siemens PLC controller and a backoff PLC controller, and then you need to exchange data for different parts of the machine between those two PLC devices, of course you can use this product in order to read or write variables between backoff and the Siemens PLC. Of course, there are always different possibilities, like also different communication protocols that allow you to do so. You can also go to the Fieldbus layer and use Profinet or Profibus to exchange data between the two PLCs. You can use OPC UA, client-server architecture to exchange data, and now you can also use the native S7 communication protocol to read or write variables between the devices. But this product can also be used in a brownfield scenario. So I give you an example. So if you have a machine here that is exclusively controlled by a Siemens CPU, maybe an S7 300, of course you can place an edge device in front of this S7 CPU, and then you can aggregate and collect the data from the S7 CPU on that edge device. So the question is, so what kind of use cases do we have here that can be solved using this brownfield scenario? So a typical retrofit use case would be, of course, first of all, to collect the data, then to aggregate and transform the data, maybe here on the edge layer. Maybe you want to push the data to the cloud, to Microsoft Azure, Amazon Web Services, or maybe to a customer cloud system. Maybe you also want to analyze the data directly here on the edge device before you send the data up. But you can also do an OPC UA retrofit using an edge device. So for example, if you have here on this device, maybe you do not have an OPC UA server, but you want to have OPC UA on your machine, you can do an OPC UA retrofit using an edge device. And the question, of course, is what kind of software tools do you need in order to solve those different use cases? And the answer is very easy, because the TwinCAT automation software suite provides all the tools and all the protocols that are required to solve all of these use cases. So for example, you could have a TwinCAT runtime that aggregates the data. You can have a TwinCAT HMI that visualizes the data on the edge. You can use a TwinCAT Analytics to analyze the data, or you use, like you see here, the modules in purple. You can use our connectivity protocols to forward the data to other devices, other systems, for example, to the cloud. In addition, you can also use Docker containers on that edge device. Maybe you want to host an AWS IoT Greengrass on there, maybe an Azure IoT Edge, or maybe the customer says, hey, I have my own application that I want to deploy and host in a Docker container environment. And of course, this allows the customer to do so. So in order to show you how the TwinCAT S7 communication protocol is actually being handled inside of TwinCAT, how it can be used, how easy it is to use the TwinCAT I/O device, or how easy it is to use the PLC function blocks, I would like my colleague from Berlin, Jannik, to give you more information on that and to show you how it's actually done.
Yes, thank you, Sven, for your great introduction. For me, also a warm welcome to our webinar, in which I'll give you a practical introduction into our supplement. Well, I want to do this through an example. Let's approach, we have a brownfield scenario. There's a machine with a S7300 running, a S7300, like I have here on my desk. This controller is connected via Ethernet with the company network, or in my case with my home office network. On the other side, a field bus is connected. In this case, Profinet, that's attached to, what a surprise, a backup bus coupler EK9300 with some terminals. Also, there's a backup controller in my network, a CX2020, and my laptop as an engineering system. Now we think about a retrofit use case, in which we need some data from the Siemens controller. The reasons for that could be very diverse. Sven has explained us before. At this point, S7 Communication protocol comes into play. But before we actually use it, I want to show you the protocol stack, not in detail, but when you are aware of it, it's totally easy to create a system manager configuration. So let's have a look. As you can see, this protocol is based on TCP/IP. On TCP, we have TPKT, COTP, and on the top the S7 COM layer that provides exchanging data with the S7. Like I said before, the functionalities of these layers aren't in our scope today. Let's move forward and have a look how this stack is represented in our TwinCAT world. Things are much easier here. The Ethernet layer is represented by the multi-protocol handler. TCP and IP merging in our TCP UDP RT driver, and the remaining layers converge into the S7 communication supplement. The supplement, again, consists three components that we consider in detail later. Short preview, there is a connection which allows us to build up a link to S7 and two types of requests to exchange data. The main difference is the way how they get triggered. Right, and with this picture in mind, we will configure our system manager. Let's start TwinCAT XAE. Here you can see a small prepared system manager, which is connected to a CX on my desk. The first step is to add an Ethernet layer. That means we need the multi-protocol handler, and we find it under the category Ethernet. Now we get asked on which physical port we want to apply the handler. In my case, it's the X0. The next object is the TCP/IP stack. You won't find the stack under New Item, it's under Add Object. Here under TCIO Other Modules. Then we can add our connection with Add New Item, and we find it under category S7 COM. The S7 connection needs some parameters: the IP address of the controller, the CPU type, rack and slot. Most of you will know what rack and slot means, but to be sure, Siemens controllers are plugged together on a rail with a backplane bus. That's the rack. And the slot is the position where the CPU is located. Normally slot 1 is the power supply and slot 2 is the CPU. So either I know all parameters or I have to discover them with the TIA portal, which I will show you next. Here in TIA, under the item Online Access, I'm able to find all my S7 controllers in my network. In my case, I have to search them with my wireless adapter. There is my S7 300 I showed you in the beginning, and we see the IP address. Perfect. When I go deeper in this tree and click on Online and Diagnostics, we find the other informations we need. The rack number 0 and the slot 2. Okay, let's type in our configuration data. S7 300 is right, rack 0 is right, and we have slot 2. So under our connection we have input and output variables. The variable state shows us if we are connected or if an error occurred. To demonstrate this, I click on Reload Devices, and we can see that the state jumps to 40, which means we are connected. When we have an invalid configuration, let's say I use the IP address of my router and click Reload again, we can see that the state is now F1. That means we have a TCP error. And the error flag is true as well. Now we have the possibility to restart the state machine with a reset variable, but rather I fix the address and we continue with requests. Let's begin with the cycle request because I think it's more intuitive. Like the name tells us, we are able to set a cycle time. I think 100 milliseconds is a good value here. In the other two pages we can configure data points we want to exchange. Once I add some entries, they will appear under the data area write to and under read from S7. For our first example, we don't need all of them, so I delete them. There is a free selectable name, a data type, and some particular S7 parameters. First, the data area. So, is our data pointer input, output, or a flag variable? The next entry contains the byte offset. And if my variable is a boolean, I can set a bit offset, 0 to 7. And if we select data block, we need to configure the ID. Now we can read an actual value. The Profinet coupler contains a cycle counter as the process data. Data type is word, and we find the counter in the input data area. And the address is, in our case, 256. Okay, I click Reload Devices and we watch our value. And yes, the cycle counter increments as we expected. The request provides some more variables. Under status, we find a receive counter that increments with each incoming response. And an error ID that helps us finding out what's going wrong. In the first nibble, we can see where the error occurred, via read, write, or in connection. Then follows the error class, what's happening, and the last byte contains the ID of the data point that's causing problems. Also, we find a flag named write enable. With this flag, we can avoid that we write our initial data into our remote controller while startup. Right, let's move ahead to single request. Of course, our cycle time page is missing here. Therefore, we found an additional variable under control, the sendRequest. The logic behind this is following. If sendRequest is one increment higher than receiveCounter, the request gets triggered. PLC implementation is now straightforward. If I want to trigger a request, I increment sendRequest and wait until sendRequest and receiveCounter are equal. I want to show you another feature that works for cycle request as well. There are two buttons to export and import an existing configuration. Here I prepared a configuration of some values of data block 2 on my S7 300. Now I activate this configuration. Increment sendRequest. ReceiveCounter has the same value, seems to work well. Let's have a look on our read values. Yes, works fine. One brief look at the import-export file format, because it's quite simple. You can see it's a list of the configuration data separated with a semicolon. That makes it very easy to edit this file with a notepad or Excel. Therewith, the System Manager path is complete and we move on to PLC Library. Before, I delete all these objects until the TCP UDP RT driver, because we still need it in the PLC. At first, we need a PLC. I name it S7 Com. And we need the SDM Library. It's located under Communication, way down. There it is. Here we found all these components we know from the System Manager. A connection and two requests. Also, the input and output variables are familiar to System Manager objects. Additionally, there are execute, busy, and error flags. And each function block has an error text as output. Let's start coding. I begin with a standard pattern that has following structure. I will copy the code to main. There is a state machine, an area to call all function blocks, and at the end, an error handling area. The state machine starts with 0, the init state. From here, we're going to reset to idle state. -1 is reserved to error cases. From here, we can go again to reset back to idle. Now we add some application code and begin with connection. Therefore, I declare an instance from the S7 connection. This FB needs a constructor parameter, the object ID of our TCP UDP stack. We have two opportunities here. The easy way is to copy the object ID and paste it in our declaration code. Of course, with the right notation. Or, the elegant way, I add a new variable for the object ID and pass value here. Now I can set the TC init symbol attribute to the variable. When we build the PLC, this variable can now be found under PLC instance at the symbol initialization page. Here I can easily link my parameter to TCP UDP stack. back to our main file. Let me close the logger so we can see a little bit more. Now we call our connection here and ensure that the connection gets closed when we are in reset. So we set execute to false. Furthermore, we implement an error routine in case of error. If we have a problem, we build an error text and set state to error. Now we need a flag to establish a connection to a S7. In idle state, we check if bconnect is true, and then we set our connection parameters. IP address will be handed over as a string, and S7 CPU type is an enum. Now we set execute to true and jump into a new state. Here we wait until our connection is established. If so, we jump in another new state. So far so good. Let's build the application, activate configuration, and start the PLC. Init is done, and we stand as expected in state 1, the idle state. Now I write bconnected true and wait for connection. This takes more time as normal. The IP address is wrong. I fix that. Once again, login with download and login, start, be connected to true. Yes, this looks good. State 20. We are connected. Perfect. Then we add a request. We start with cycle request as well. First, we need an instance of our request. Call it under FBA calls. And add a error handling for this request and add the reset code. So set the be execute to false. The request must now add to connection. Therefore, it provides a method called AddRequest. There we can handle over the request. Adding read and write variables work similar like that. Both requests provide methods called addRead and addWriteVar. For data types like Boolean and string, there are related methods. Let's reuse our old example and read the cycle counter with this request. For this, I add a new variable, a word, and call addReadVar. The first parameter expects a pointer to our variable. Then we pass the length. After that, we set the byte offset, 256. The next parameter is the data area, and the last parameter the data block ID. We don't use a data block right now, so we let this 0. Okay. Now we use the transition from wait to connection to is connected to start the request. Cycle time is set to 100 milliseconds and execute is true. Let's log in again and set be connected to true. and we see that our counter is running up. Last but not least, we want to write a data point at the Siemens controller. Therefore, I declare two single requests, one for reading and one for writing. For sure, we need two flags as well to trigger these functionalities. Then I paste the declarations of the variables we want to exchange. And now comes the known procedure, call the FBs, add the error handling, and paste the reset code. So here in the init state we have to add the requests to our connection. Data block 2 contains at byte offset 0 a byte and at offset 2 a dword. These data points we want to read and write. Therefore we add these variables with the methods addRead and addWriteVar. In state is connected, we check if one of our flags is set to true. Then we set the corresponding execute of the single request to true and jump to a state where we wait for the request to be done. And jump back, of course. Okay, let's test our new code. After setting B connected, the cycle counter is running. That's a good sign. First, we trigger B read to see what's on our controller. The byte is 42 and the dword is 100,000. Now set the byte to 23 and dword to 555,000 and 555. Yet I trigger write and then read, and we see that our read and write values are equal as expected. Yes, that's it for my part. Back to you, Sven.
Thank you very much, Jannik. I think this was some very good information to actually see how TwinCAT S7 Communication can be used inside of TwinCAT to collect data from an S7 PLC and aggregate the data inside of the TwinCAT PLC environment. So, but what can I do now with the data? Now that I have the data in my PLC, of course I can visualize the data, analyze the data, but we also talked about forwarding the data to a cloud system. And this is what TwinCAT IoT is all about. TwinCAT IoT is a product family that can be used to establish a data communication with the cloud system. So you can use almost any kind of public cloud service provider. You can use private cloud systems if you have a cloud in your own company infrastructure. And it is based on standardized communication protocols like MQTT or OPC UA. So as an example, I picked two products from this product family. So the first one is the IoT communication product TF6701, and it's a set of PLC function blocks that allow you to establish an MQTT communication with a message broker. The communication can be secured using TLS mechanisms, so you can encrypt the payload of the messages, you can use client-server authentication, and of course, it supports also different data formats. So you can use a binary data format, you can use a JSON-based data format or XML-based, so whatever you have in mind and whatever your application needs. The second product that I picked here is the TF6760. It's our HTTP REST client that allows you to establish an HTTP connection to a REST API. So if you have a web service out there that offers an REST API, you can connect to this REST API and then trigger HTTP commands like get, post, put in order to exchange data with this REST API. Of course, the data communication can also be secured using TLS mechanisms. So it's very similar to our MQTT communication protocol that we just saw earlier. So the different, let's say, connectivity scenarios that we can solve using TwinCAT IoT, of course, everyone will believe us if we tell them, okay, you can use TwinCAT IoT to connect your newest machine generation using TwinCAT 3 to the cloud. So this is what you see here on this side of the graphics. So you can trigger MQTT and HTTP commands directly from within the TwinCAT real-time context. But of course, we saw earlier that you can also use an edge device that you can place in front of your existing machine application in order to connect this machine application to the cloud. You can use the same edge device also for aggregating third-party devices to the cloud, because we do not only use proprietary communication protocols, but also standardized communication protocols like OPC UA. So, but what can I do now in more detail with the data when I send this data up to the cloud? So how would a technical, let's say, architecture diagram look like? I would like to give you an example here. So let's imagine that we want to connect an existing S7 PLC device via an edge device to the cloud, because we maybe have, like we saw earlier, again, we have a machine here, a machine application, which is controlled by a Siemens S7 300 PLC. And then we place our edge device in front of it. Of course, it is a back-off industrial PC as an edge device, for example, our C7025. And then we have, inside of this edge device, we have our TwinCAT products running, for example, the PLC runtime that aggregates the data, and our TwinCAT S7 communication product that is getting and acquiring the data from the S7 CPU. And then on top of that, we use our TwinCAT IoT product in order to connect the data to the cloud. So what kind of cloud services can it be? I talked earlier about supporting many different public cloud service providers. So our customers tell us, hey, I want to connect my machine application maybe to Microsoft Azure, Bosch IoT, IBM Watson, or Amazon Web Services. And it can also be like a private cloud system, or let's say a customer cloud system that is maybe built based on Amazon Web Services technology, like you see here. So there are different kinds of services on Amazon Web Services available, like Amazon Kinesis, Amazon Simple Notification Services, IoT Core, or AWS Lambda that you can use to analyze your data and enrich the data in order to get a benefit out of it. But of course, you can also forward the data in parallel to our back-off TwinCAT Cloud Engineering environment, which is a back-off cloud service. And on this cloud environment, you can then maybe use our TwinCAT Analytics software in order to analyze the data. So TwinCAT Analytics provides a set of different algorithms in order to build an analytics network, which you can then use to analyze incoming data streams. And in this example, data streams that are coming from your S7 CPU. And on top of that, TwinCAT Analytics has a very nice feature, which is called the one-click dashboard functionality. And this feature allows you to automatically generate an TwinCAT HMI project based on the analytics network that you just configured to analyze your data. And then you can host this HMI project directly in your TwinCAT Cloud Engineering instance in order to visualize the data based on an HTML5 web page. So at this point, I would like to thank you for your attention. So now we would like to answer your questions that came up during this webinar. Thank you very much, and see you soon.